Recording. Okay. So I haven't said it. Fortunately, I haven't said anything important yet. So another type of conductor is this dielectric material. Transmission lines typically support. So we have to use wave theory when we're dealing with transmission lines, and this is an introduction. We'll get into the specifics as starting today and continuing in the next couple weeks. A propagation mode known as TEM or TEM, and that stands for Transverse Electromagnetic. And in this mode, the electric and magnetic field vectors are perpendicular. They're perpendicular to each other, but also to the direction of travel, direction of propagation. And this is where the transverse is another way to say perpendicular. So both fields are at right angles to the direction of propagation. So that means in a coaxial cable, we'll see that the E field is directed from the higher potential to the lower potential. So these would be, again, these vectors are actually everywhere in space. And hopefully in the homework you're getting some practice sketching these fields. But the E field would be like that. The B field is in concentric circles actually around the inner conductor. And so it's in a clockwise, as I've drawn it, it's in a clockwise direction around that inner conductor. So this would be the E and B fields for a coax. In this case, I'm showing you a slice through the coax. The coax is actually running into the board. The signal in this case would actually be propagating into the board. Okay, so we'll talk a lot more about that. And then in a microstrip, you've got the ground plane and then a conductor. The E field goes from the conductor, and the B field is transverse to that. B cross E cross B is actually into the board. I'm showing the conductor actually running that way. And so the signal would be running into the board there as well. So this is microstrip. And again, we will typically use the term transmission line when we're talking about this particular mode of propagation of the wave where the electric and magnetic fields are transverse to the direction of propagation. At higher frequencies, you run into more complex modes of propagation where the wavelengths are very short, and you run into what are known as transverse electric, transverse magnetic modes of propagation. And you may or may not have actually seen something like this, these metal tubes. They're called waveguides. They're typically used at microwave frequencies for transmitting a signal from, a source to a horn antenna, some sort of antenna structure. And you can find connectors to connect like coax to a waveguide, but radar frequencies, microwave frequencies. And then another case where you'll run into, we typically don't call these transmission lines, but in fiber optical cable, and light is a form of an electromagnetic wave. Okay, so there, you typically the propagation modes are usually more complex than just this transverse electric magnetic mode. Okay. So we want to develop, again, this model for the transmission line. Typically, this is always we want to connect some source. It may not physically be a voltage source, and source impedance, it might be, it typically is, maybe the output of some transistor or power amplifier or something like that. And then we connect that via our transmission line to something that we call our load. Now this may be the next amplifier, maybe in this class, typically an antenna. And assume our transmission line has a length L. We'll model transmission line as what's known as a two-port device. And you've seen these two-port device models previously. Transistor amplifiers are often modeled as two-port devices. There's an input port, and that just means a pair of connections, okay? The input, like for a transistor amplifier, you've got typically your ground and your signal, and then you've got another pair of output connectors, okay, for the amplified signal. Again, the amplified signal and then a ground connector. And then you've got this model with an input voltage feeding the amplifier, and then it produces an output voltage. So VL, ZS. So this is VS and ZS, of course, represent the Thevenin model for whatever comes before the transmission line. So in this black box is where we want to come up with, a model for our transmission line. Again, this is new. We've never done this before, right? We've ignored the effect of a wire and treated it just like a node. The voltage at one end of the wire is the same as at the other. The current in is the same as the current out. Things are different at high frequencies. So the parameters we'll be working with that we'll use to characterize that make up our model. These are the physical characteristics of the transmission line. And ultimately, these will become constants in our model. Beta is the phase propagation constant. And it has units of radians per meter. And we've already looked at beta before. It's 2 pi over lambda. Now what may be a little different here is, lambda in meters is c over, or is the propagation velocity divided by the frequency. So what we looked at before was propagation in free space, and was the speed of light divided by frequency. Well, in some of the materials, the propagation speed is not the speed of light, it's slower than that. So, but it's still the propagation velocity divided by the frequency is lambda, and then beta is 2 pi over lambda. And then there's an attenuation constant. So beta actually allows us to calculate the phase change down the transmission line. The number of meters times beta would give us the phase change down the transmission line. The attenuation constant has units of meters to the negative 1 power, or 1 over m. This is going to appear as an e to the minus alpha z. So this represents a change in amplitude down the line. Okay, take the length of the line, multiply it by alpha, then that change in amplitude is e to the minus alpha z. It's an attenuation, implying that the output amplitude is going to be smaller than the input amplitude, due to resistance in the line. So, and then the third main parameter we'll be working with is Z0, the capital Z. This is called the characteristic impedance of the line. It has units of ohms. And this gives us actually our relationship between voltage and current, just like impedance in circuit theory. So we'll run into these. Lump element model. The first thing we want to do, though, is actually come up with a model for the transmission line. And our model is a differential equation model relating the voltage and current in the transmission line. You might expect that. That's how we have from circuits. So the approach of coming up to this model is we're going to split the transmission line into small segments. Each segment here is of length delta z, and to get the differential equation, we're ultimately going to let delta z go to 0. And then in each segment, we're going to model what's going on in each little segment using a resistance R prime delta Z. R prime is actually resistance per length. So R prime delta Z would give us the resistance. And we're using this model for each one of these little segments, for each one of these little delta Z's. And L prime delta Z similarly would model the inductance. So R prime delta Z represents the resistance in that little segment, in that little length. It actually represents the resistance in both wires, but we lump it together in our model as just a resistance in one wire. And we'll see when we start talking about inductance that actually just a current flowing through a conductor acts like an inductor. there's a magnetic field set up, there's energy stored in that magnetic field. That is an inductor. So this models that effect. You know, again, for what we've been using, both of these are short circuits in our traditional model for a wire. There can also be what's called a leakage current between the two conductors. You know, a small amount of current, even though it's an insulating material between them, there can be a very small amount of current flowing through that insulating material between the two conductors. And we model that as, here G is our symbol for conductance. So we model that as a conductor. You could use a resistor there, but the equations actually are a little simpler when we write them in terms of this conductance instead of the resistance. Now this is a completely different resistor than R prime is. R prime represents the metallic resistance in the wire. G prime is the resistance between the two wires. And anytime you have two separated metallic conductors, there's a corresponding capacitance between the two conductors. So this is the little circuit model we're going to use for every little delta Z. So R prime is the resistance per length. It would have units of ohms per meter. L prime is the inductance per length. We have units of henries per meter. G prime is the conductance per length, Siemens per meter. And finally, C prime is the capacitance per length, and it would have units of farads per meter. So the next step, and this is equations. This is the last thing we'll do today, because I think we'll get out of here a little bit early. But it's a good stopping point. And I give you some homework problem working with these set of differential equations. They're called the Telegraphers Equations. So let me go back here to our model. And we've got an input voltage. But our voltage now is not just a function of time, like it typically is. It can change with distance, and we're letting Z be the distance down the line. So the output at the same time is not necessarily the same. It's going to be a little different because it's at a different location in the line. So we let that voltage, we call that VZ plus delta Z. And then similarly, this current is IZT. This current is IZ plus delta ZT. Again, they're going to be different. So from Kirchhoff's voltage law, I'm going to start right here at this point. Normally I go clockwise doing these Kirchhoff's voltage law things, actually, yeah, we'll go clockwise, but we'll start here. And so it's plus V plus delta ZT, starting here at this point. And then we're going to go clockwise around this outer loop. And we get minus V ZT, right, plus, minus, and then here I get, for the resistor, I get an IR drop. I'm going in the direction of the current. So that's going to be R prime delta Z times IZT. And then for the inductor, the voltage is L di dt. So for the inductor, it's L prime delta Z. And then it would be the derivative with respect to time, but since now the current is a function of two variables, it's a partial derivative of IZT is equal to 0. So I'm going to put the voltages on one side and the currents on the other, so come up with a relationship between the voltages and currents. So I'm going to move the voltages to the other side. So I'll have VZ plus delta C T minus VZ T. And then I'm going to divide everything by delta Z. So this is what I get when I move the voltages to the other side of the equal sign, right? A minus in front of that difference. And then that's going to be equal to R prime IZT plus L prime, the partial derivative with respect to T of IZT. So if you look at this term in parentheses, that should remind you of the derivative, right, with respect to delta Z. It becomes the derivative in the limit as delta Z goes to 0. That's the definition of the derivative. Now here again, V is a function of both length and time, so it becomes a partial derivative in the limit as delta Z goes to 0. We get partial with respect to Z of VZT is equal to R prime IZT plus L prime partial with respect to T of IZT. This is one partial differential equation relating the voltage and current at any position along the line at any time. Similarly, applying Kirchhoff's current law here at this node, we've got I going out, IZ plus delta Z going out. I've got this IZ going in. The current flowing through the capacitor would be the capacitance times dV dt. And then the current flowing through the conductor, it's not V over R, it's V times the conductance. The current flowing through the conductor would be this voltage times that conductance. So I go through these same steps, through the same set of steps, and I get another differential equation. I'm going to skip the derivation. IZT is equal to G prime VZT plus C prime partial with respect to T of VZT. Okay, let me actually number these as equation 1 and then equation 2. And these are equations 1 and equations 2 are the Telegraphers equations. Although I don't know if telegraph lines exist anywhere in the US, I think telegraph, it still is used maybe in some places in the world. But these equations were originally derived to describe how the voltages and currents behave on telegraph lines. Okay, which again, they're the telegraph lines, right? Telephone lines can be, very long. So these are the Telegraphers equations. Now, again, it's like partial. There are a couple pair of partial differential equations. So, but don't freak out on me. You know, in most of our courses, we try to figure out how to avoid actually solving direct differential equations, at least using the techniques in your differential equations course, and look for simpler methods. And that's what we'll do here. And it's a little more complicated than what you've encountered in circuits, but we won't be directly solving the differential equations, okay, at least every time. So they simplify if V, Z of t, and I, Z of t are sinusoids. Then we can write where V bar Z is our phasor. You know, it's a complex number, right? But from Euler's, you know, so it would have an amplitude and a phase angle. And then so the real part of this would be that amplitude and then cosine omega t plus whatever that phase angle was. This is, V bar here is what we call the phasor. But now our phasor amplitude is a function of distance. You know, previously it was just in circuits, it's just a constant. It's a complex constant. Now we're generalizing that a bit. It's a complex constant that's a function of distance down the line. And then similarly, Iz of t can be written as omega t in terms of our I phasor, which is now a function of time. So where Bz and Iz are phasors. The equations become so you write them in this form, and then you can do the time derivatives here with respect to, you know, all the time dependence is now on this e to the j omega t. The derivative of that is just j omega e to the j omega t. When you take derivatives with respect to time. So all the time derivatives actually go away, and the equations simplify. R prime plus j omega L prime I Z. And the second equation becomes minus partial with respect to Z, I bar of Z is equal to G prime plus j omega C prime BZ. Still not trivial looking, but we're seeing some things that we've seen before. You know, that's an inductive impedance, j omega L. This is a capacitive susceptance. Susceptance is the reciprocal of impedance. So the impedance of a capacitor is 1 over j omega C. The susceptance is just j omega C. Just like conductance is the reciprocal of resistance. So here, you know, susceptance times voltage gives you current. So we see some things here that look like our circuits. Still a little bit bothered by this partial derivative with respect to Z over here. Still have to figure out how to come up with solutions to these things. But we'll start that actually on Monday. I think the homework problem I asked you to plug into, I give you a particular V and I, a sinusoidal, and to plug into this equation, just do derivatives. And then come up with a relationship between, it's really between the I phasor and the V phasor. So just to get you to playing around with these equations a little bit. But that's it for today. And see you on Monday. Have a good weekend. I guess according to the news I've heard that